So thank you everyone for coming tonight. It's our 5th edition. We are very excited for this new session. Very excited to see more and more people coming, and we hope that you find interest and pleasure in coming every month. Just want to say another thing. We also have a Facebook group and a YouTube channel on which you can find the slide and the videos afterwards. All the videos are available there. And if you have any suggestion, please come to us and explain whatever improvement you think we should add to the meetups. So today we're going to go on talk about homomorphic encryption and SGX. And to start first, we want to thank Enigma for sponsoring the event. And yeah. And thank also them to come and explain a bit of what they're doing, and especially with this very cool, interesting tech, which is SGX. So I'm going to call Moria and Isan if they can come and start presenting. Thank you so much.
Hi.
Hi. We are very happy to present here in Enigma. We are a small company. We are very cool. We resided in the US and Tel Aviv, Israel. And we'll show you the part of the work we did in the last year. And especially common release called Discovery. Okay, so I'm Moria Abadi, and I'm Moria Abadi. And my main work in Enigma is around WebAssembly, secret contracts, and the Enigma engine.
Nice to meet you. I'm Isan Rifkin. I work in Enigma mainly on the peer-to-peer networking and SGX stuff that will be presented.
The outline of this presentation is follows. First, we will do some introduction to Enigma, and we'll understand what problem are we solving. Then we'll introduce an Intel SGX technology and how is it used by Enigma. The third part will be about WebAssembly standard and how. What? Okay, and how the standard is supported by Enigma engine. And the last part will be diving into Enigma solutions into more depth. So what Enigma tries to solve. As we all know, the data on blockchains is public, and this is not suitable for all use cases. For example, we want to build a voting system above a blockchain, so we want the votes to be private. While maybe we want the result of the voting to be public, but the votes the calculation of votes, we want them to be private. Another example may be blockchain-based credit score. This system uses very sensitive private financial information about the users, and also should be private. So Enigma is a P2P permissionless network that enables secret computations. It is economically incentivized, which means that the workers or nodes in the Enigma network are rewarded for the work. And this is compatible with Ethereum. We will see later what it does exactly. This is very high-level architecture of our system. On the bottom, we see a user. This is who wants to trigger a secret computation. On the right-hand side, we see Enigma P2P network. The nodes of this network execute secret computations and distribute the results over the network and return the output to the user. And on the left-hand side, there is a third component, which is Ethereum. So why we need Ethereum? Enigma P2P network is not a blockchain with consensus, but we want the computations be done over a blockchain. So we use Ethereum blockchain for verification of the results. Okay. Now the fun part.
Hi. Okay. So before we dive into SGX, can you raise your hand if you know SGX? You keep it up if you worked with SGX. So what we're going to cover today is just a very high-level overview of generally what is SGX, because it's essential to understand the Enigma protocol, and then we'll go a little bit into what we do with SGX. So before we dive into what SGX is, let's speak about a non-SGX world. We have different ways to secure applications today. We can encrypt stuff, right? We can use hashes to detect changes. We can write different firewalls and things like this, and we can secure our applications and communication between computers. But no matter what encryption we use, at the end of the day, when some machine computes over data, it computes over clear text data, unless it's fully homomorphic encryption. And then anyone can see what's going on in the registers in the CPU. You have different tools, CPU tracer and debuggers and things like this, and you can literally see the clear text. And this is a problem. It doesn't give us the hardware level security. So yeah, you see this, right? Now, if you guys know Ledger, it's a little bit like this, meaning we have some trusted hardware that computes stuff. So in a Ledger, in Ethereum wallet or Bitcoin wallet, we have the private key. We can send a raw transaction inside. The transaction will be signed inside the Ledger, and we get the blob outside, and the private key never left. So we have this notion of a trusted computing area and untrusted, right? So you can think of SGX as a ledger, but a very smart one, and it lives inside the Intel CPU, every Intel CPU from generation 6 and forward. Now, the Wikipedia definition is, if we go through it, it's Intel SGX is a set of CPU instruction codes from Intel that allows user-level code to allocate private region of memories called enclaves that are protected against running at higher privilege levels. So we have different CPU instructions. New instructions, those can be called from ring 3, meaning user, not privileged user, and they can allocate private regions of memory in the computer that other privileged processes cannot access. So it's kind of, we have this secret area of memory that no other processes can share with. And it can allow different things like remote computation, for example. So if we look here, we have me and my granny, and the bank uses an enclave. And now this is just a use case for remote computation, and I want to send her $50. So the bank could use an enclave to store the transaction details. I could encrypt the password and the amount with the password that only lives inside an enclave, which is an instance of SGX. I could send this to the enclave, it could update the registries, and I know for sure that no one saw this data besides the enclave, and this is one of like a very simple use case. But mainly what SGX gives us is isolation. We have this process that is running, but nobody else can go and see what's going on. So if we look in the RAM, we will see another process, but it's pointing to an area that is not visible neither to us or to any other privileged processes. So we get isolation on the hardware level. Now, as a quick glance, every SGX instance is called enclave, and we can reference it with an ID. And every SGX application is created out of 2 parts. We get a trusted part, which is, hopefully you guys use in Linux, so it's an SO, but it could be also a DLL on Windows. And we need to interact with it. So we always have an untrusted part, which would be some binary written in C++ or in Rust or in C that interacts with this SO and calls different methods into it. So this would be computed in the private region memory, this would be the enclave. And this is the untrusted part that would be interacting with it. Okay, so we have isolation. What else? Okay, so enclaves are stateless. And because they're stateless, it's a problem. It means we cannot do much. So Intel came up with a solution. They say, we have now SGX sealing. Basically, the sealing, what it does, it's a pretty word for saying encryption. But for encryption, we need keys. And for keys, we need to generate them. So it's an interesting idea of how we can do sealing. First of all, the keys are generated in a factory. Here's the factory. And Intel does their best effort to do it in mass production. They burn the keys in the hardware. And they don't link which computer belongs to which keys, because they don't even know which country it distributes to. So basically, they produce a lot of computers, they burn a lot of CPUs, they burn the keys inside and distribute this all over the world. This is how keys gets created. Now, when we, the writers, when we use enclaves, we want to get those keys, for example, to save some state on disk for later time, when the enclave will be loaded again, and it can read some state data and things like this and see it. So we need, for this sealing mechanism, we need the key derivation function. It's not like the keys are accessible to us for signing or encrypting. So we have this key derivation function that comes with an SDK. It has a security version and other stuff, and generally we can derive different keys for it. One of the use cases is the sealing, meaning keep stuff that only enclave can read. Only enclave, and only enclave with a specific code. So it's not like any enclave on the system. Okay, so how sealing works? Basically, the green box is a trusted part. We can take some data. We can call this function seal data from the API, and we get a blob back. Then we can call the untrusted part and tell it, okay, take this blob and save it to a database. The key never left the trusted part. Then, when we want to read the data again, we do the unsealing. In the untrusted part, we load the blob from the database and pass it to the trusted part as a blob. And only the blob can see the data. It depends on our implementation, but the keys never left the enclave. Okay, now we have state. It means that we can save bytes into the disk and read them later, and only our enclave with our code that we wrote can see this. Okay, so what we covered so far, enclaves are instances of, you can have, enclave is an instance of SGX during runtime, some specific code, some specific SO. You can have multiple enclaves on the same computer. SGX application always has trusted and untrusted part, and we have sealing. Now, we've covered isolation, we've covered sealing, that will allow us to have state. Another thing we need to do is, we're a network, right? So we need to know that someone on the other side is a real enclave. So we can share secret with it. Maybe we can trust it with some secret computation. So we need a way to know that this is enclave, and this is a remote attestation process. Now, remote attestation is something general that Intel uses in their own way. You can read, there's a lot of specifics about it, but basically it lets you say that, okay, I'm speaking to an enclave, even if the server, so-called server, is untrusted. Like, maybe it's compromised. And this allows us to do different cool things. So how it works, very generally, you have some user, and he's going to this computer, and he's like, prove to me your SGX. Give me a quote. I need a quote from you. So he gets a quote. The quote is encrypted. Got nothing to do with the quote. We're sending the quote to a specific service that Intel provides. It's called IES. This service will verify the enclave without knowing who the enclave exactly is. It's based on something that's called EPID, and it will return me a report. The report will include different details. For starters, it will include the hash of the code of the enclave here. It will include the version number of the enclave, and it will include different security flags saying stuff like, oh, you can trust this enclave, or you cannot trust this enclave. And this would be the report. Behind the scenes, there's more stuff. So the server would be in some untrusted part. The blue box here is different enclaves that come with the system that are part of the platform. So the SDK would interact with those. And there's more steps in here, but this is generally the process. Okay, but at Enigma, we do things a little bit different. We want to use this, but as we all know, or some of us know, in a decentralized network, interactive processes are bad because it's not efficient, it's hard, usually it ends up being centralized, so we need a non-interactive way, and this is what we did. We created a way for non-interactive verifications of different enclaves. So, to every quote, we can attach a key. This key is generated inside the enclave, the private key, and we attach it to this quote here. And this is what we do. This would be used for signing later for everything. And then nodes would produce a quote, ask for a report from Intel. Everything is signed by Intel, and store this on Ethereum. Ethereum is another network. And that's all. From this point on, this report gets verified on Ethereum. We have even a RSA verification. And on Ethereum, we verify the chain of trust. We extract the signing key that was generated in here. And everything now is kind of like an identity, meaning I don't really know anything. I just know that this key was generated inside the code base that Enigma wrote, and it's verified by Intel. That's all we know. Now, we don't need the process again, because if everything is signed with this key, we can trust that it was generated from within an Enigma enclave. So basically, this process happens once during something we call a registration process. Enigma's use case for SGX, we have attestation. So as we just said, we want to know that some signing key belongs to our code. Another thing, we want to force correct computations. So we compute stuff inside the enclave. And this is what Moria will present in a second. And another thing, we have sealing, just what we show. So for example, this signing key, we need to save it on disk and load it later to reuse it every time to sign different messages and computations. And in a high level, this is how we use an SGX. Woo.
Okay, let's talk about WebAssembly or WASM. First, before understanding what WebAssembly is, I want you to understand what is it for. Before WebAssembly, the common way of writing web applications was using JavaScript or a language compiled to JavaScript. This was the only language naturally supported by all the browsers. But there is more and more requirement for web applications. More and more languages are required to target web. So WebAssembly is designed for this goal, to serve as a compiler target for other languages. General purpose, very popular languages like C++, Python, Java, all of them already may be compiled to WebAssembly, and this list is growing. WebAssembly is supported by all browsers. So the WebAssembly is actually a standard of bytecode that may be deployed on web and be run in all the browsers. It was developed in W3C, which included representatives from all major browsers. It is language, hardware, and platform independent. And there is a very cool feature. If you think about that, we have one formal semantics now for WebAssembly for any web application. So instead, writing formal verification tools or code analysis tools for different languages with different semantics, all this effort can be unified for WebAssembly. WebAssembly is easy for debugging. There are also other nice features of WebAssembly. But as I said, maybe the main interesting feature is that this bytecode is deployable, and nothing in WebAssembly design is not related directly to web. So WebAssembly may be used beyond the web use case. This is how Enigma uses WebAssembly. Enigma uses WebAssembly as a language for secret contract. What is secret contract? It's a code that will be deployed on a network, on an Enigma network, And then the computations may be called, may be executed on this code. It resembles smart contracts in Ethereum. For those of you who are familiar with this term. Okay, it's possible to write directly in WebAssembly, but it's a little bit difficult. It's not like a regular assembly with a set of instructions that it's very difficult to understand by a human. WebAssembly has structures like functions, ifs, and so forth, but still it's difficult. So we needed to choose a language for writing a secret contract. We chose Rust. It's an efficient language. It's a relatively new language, but its main feature is that it is memory safe. And in the future, other languages that may be compiled to WebAssembly may be added. Okay. Now let's see a little bit anatomy of our runtime and how the WebAssembly is executed. This is the worker, the node of our network. And as you saw, it must have SGX. All the runtime is resided inside SGX. The first component of the runtime is execution engine. This is the engine that takes a WebAssembly code and may execute. Enigma also gives user services. For example, state. This is another. This is another very important component. Between the executions of the bytecode, there is a persistent state that is stored in our network, and this is the component that is responsible for that. The services has APIs. Through this API, the contracts may connect to the services. And the last component is called GAS. Rust is a Turing complete language, and therefore the execution may be infinite. We need a means to this not to happen, and the GAS mechanism is responsible for that, and also is responsible for calculating how much effort the worker did for execution and how much is his payment. The GAS mechanism is exactly the same as in Ethereum, for those of you who is familiar with GAS mechanism. Okay, so here we see the runtime inside SGX, inside the Enigma worker. This is the user that triggers the computation, and this is the Ethereum. Now let's see the process. What happens? First, the user writes a secret contract. Actually, this is Rust code. This code is compiled, and the result of the compilation is a WebAssembly code. This code may be deployed on the network, and then the execution may be done on this code. For any calculation, there is a transaction from the user to our network that triggers the computation. For the computation, the WebAssembly code and the inputs of the user come to the runtime, and the code is executed. Another feature that we have, we call it Ethereum bridge. This is connection to Ethereum. This is not the same purpose for, as I said at the beginning, for verification of the executions. It's something else, something additional. This is what we mean by Ethereum, that matches the Ethereum. Suppose somebody wants to build a voting system above Ethereum, but he wants that the calculations will be private. So he makes a smart contract on Ethereum, which will publish the results of the voting, but all the calculations will be done here privately on Enigma network. So at the end, the transaction to Ethereum may be done for publishing the calculations. voting results. Okay, now I will show you how the secret contract looks like. If you are not familiar with Rust syntax, don't panic. It's not so difficult. It's a very cool language. Okay, this is the bindings to our services. As I said, the WASM is what we give to the user. This is declaration of the secret contract. And this is the abstract interface only with the functions and their signatures. This interface should be implemented. Here we see the implementation, a very simple implementation. And this is user-defined type struct. And this interface is implemented for this struct. Here we see the function test, which calls some other function. And why I show you this, I want you to understand that anything from Rust may be used, any library and any structure here, I can define anything and just use it. Here in exec function, we see the example of using of our runtime. This is one of the services that we give to the user right into a state. Okay, the last thing that I want to show you is Ethereum bridge. For calling contract on Ethereum, the user should have its ABI definition, which is natural, and the address where the Ethereum contract was deployed. So this is how we use the ABI definition. User just needs to point where the file with the ABI definition is, and then to create a structure for this contract and to call any function. Okay? So what we've covered so far. The Intel SGX technology and how is it used by Enigma, the WebAssembly, and the secret contracts. What we will see next. First, we said that we perform secret computations, but we didn't see how is it secret. So we'll see how the secrecy of input and output is achieved, secrecy of state, and at the end we'll see how we use the consensus.
Thank you, Moria. Okay, so you've seen this stuff that is super cool to me, that we can write secret contracts on Ethereum. And our goal today is not to go into every technical detail, but to give you some knowledge so you can start maybe playing with our existing code or go explore more, right? So we're not going to dive now into every detail. And if you have questions, you can ask them at the end. Okay, so generally the workflow that you would expect from a user in our system would be, let's say I want to do some voting, right? So the user will need to exchange inputs, kind of, I'm voting for, I don't know, vote. I'm voting to someone now, and I want to encrypt my vote. So I need to do this, right? There's this stage. Then the network needs to register who voted for what, right? Kind of a state update. At the end, we want to do to tally the votes. And then what we want to do, we always, at any point, want to verify. We want to know that the computation and the state is correct. So secrecy of the inputs and outputs of the network, right? We have a user, we have a network, and we have Ethereum. The user would be connected to some gateway node. It doesn't have to be connected to somebody specific. Now, first thing we want to do, we want to know who is Batman, who will be computing now, what needs to be done. So I would ask Ethereum, who is the worker with the signing key? And Ethereum say it's Batman. Okay. Then I would go to my gateway node, and I would say, I need to do some key exchange with this node because I want to send secret inputs. So the gateway node would be a relay. We would do a key exchange. I would send my inputs through the gateway node to the secret node here. And this is how the inputs would be transmitted. And it's based on Diffie-Hellman key exchange, nothing crazy. Now, besides the inputs, we have states. And this state also is the same currently, and this version in discovery is replicated and distributed between everyone equally, hopefully. So everyone have the same state and the same encrypted state. Now, let's say the user, the worker who does the voting he updates the state, right? It's unlocked here, woo. And everybody has a green state. At the end of this process, where everybody needs to, one worker updates the state and broadcasts it to everybody else, they have now new states and encrypted states. And this is all nice and well. The user gets some output, maybe some Boolean saying success. I don't know, maybe some computation result. It could be anything. The output is also encrypted with the same Diffie-Hellman keys. And there's a problem here. How do we know that the output is correct? How do we know that the state change that affected the whole network is correct? And
so consensus. Okay, we use Ethereum consensus for verification of everything we did. And also all the important decisions are done on the consensus layer. We have Enigma smart contract deployed on Ethereum. Okay, so it is responsible for many things. The first is computation tasks. We said that there is a task for computation, so they get their unique IDs on consensus layer. Also, their statuses are tracked on Ethereum. Workers. The workers should register on the consensus layer before starting working. Should be registered and verified. Also, the selection of who exactly are going to work on which task is done on the consensus layer. You remember the user asked Ethereum who is the worker and answered Batman. This was done by Ethereum on the consensus layer. The verification, as I said, the verification that the user is trusted. So this process that Isan explained about SGX. And also that the execution is correct. For each task, the Ethereum in the Enigma smart contract holds the inputs, more precisely hashes of the inputs. And after the execution, the worker signs on all the inputs and all the outputs, and its signature is verified on Ethereum. This is how it is done on a very high level. And we are hiring. If you're interested, please send me a mail. What are your questions?
thank you.
Thank you very much.
Hi, guys. Well done. You are trusting Intel SGX. Me too, so that's fine. But assuming that you trust Intel SGX, okay, so why to utilize for consensus a blockchain which is so inefficient, assuming that it doesn't use SGX? Okay, I mean, you have your very cool network, Enigma network, and you have a very expensive and slow consensus mechanism which does not use SGX, but you trust.
So it's a great question. We ask it also, but our answer for now is it has different aspects. At the current version, we try to focus on what is important for us, which is the execution engine. So we want to be able to execute smart contracts in a private preserving way. So there will be changes, but currently what we do, we need some way to store the metadata. So we know it's an enclave, but somebody needs to store this data, and those technicalities Ethereum provides us right now and enable us to focus on the execution. And at some point, we plan to remove this extra layer of Ethereum. That answers your question. Yes, that's correct.
Function in Bitcoin, you'll use it as well.
So
you only get the state, but in Ethereum.
So let me tell you what we store.
Hmm?
Let me tell you what we store.
Okay.
We store hashes.
Hash.
Yes.
Yeah. Only hash of the. How many bits? Bytes? 256 bytes?
Yes, so we store hashes, which is 256 bytes.
Okay.
For example, let's make
So
it...
you can use any other blockchain. It doesn't matter if it's Ethereum or whatever, as long as you'll get your 256 bytes.
Yes. We also have a feature where we allow a bridge to Ethereum. So, for example, you could compute some state on the Enigma network, and because we work with the Ethereum, so we said, okay, so we have other features, and we have a bridge where we can call some other function on a secret contract on Ethereum.
No, but the consensus layer may be replaced by other consensus. Yes, you're correct.
Yeah. So it's you have your own like a side chain, which you only use the Ethereum for storage of state. Okay, thanks.
Hi. In the lecture, it seems that you rely mainly on SGX as being secure. So, but it's already known not as an architectural fault and attacks that break it.
So just to repeat the question, SGX is known to be hacked in different ways, and what do we do with it, right? So we are trying to be aware as we can of those attacks. Intel are mitigating and trying to mitigate some of them. We are, and at the same time, we are trying to rely as least as possible on the single promises of SGX. Rather, we look at this now as another security layer. And there's definitely some side channels attacks on the hardware level that are not completely mitigated yet. And we are trying to develop and think about extra mechanisms that we can add to give extra security. But for now, you're right. Definitely. Show me them. Maybe there's even ones I don't know, but yeah, for sure. What we are trying to do is to do the best with what Intel provides us, and at the same time add different mechanism overall.
Right. So I wanted to ask two questions, if possible. One is related to as it was already mentioned, the SGX had a few hacks, and there are going to be some in the future. But since you have a consensus mechanism, have you considered supporting and creating 3 different pools, one with SGX, one with AMD SCV, and another one with Trust Zone, so that you can use your consensus mechanism to mitigate attacks attacks on one platform, assuming that 2 out of 3 platforms don't get compromised at the same time with a 0-day?
Good question. Tons of knowledge here. Let me see that I understand it. You're saying there's more SGXs in the world. It's not only SGX.
Exactly. And since you have a consensus mechanism, you could use it to support multiple platforms and require that 2 out of 3 different pools of different platforms are participating.
So I think from the best of my knowledge, because there's a lot of things to do, we are working in 2 parallel ways. First, yes, because we looked at secured hardware on Android devices. But at the same time, we want to try and research approaches that will allow us to solve this algorithmically, for example, MPC, which will be less dependent on hardware.
Okay, so we can continue this offline. And another question that I didn't quite understand, or maybe you didn't cover it, I guess, is if I suspect that a node has been compromised, do I have a way to challenge it similarly to? Are you familiar with how TrueBit does it?
Nope.
Okay, so in TrueBit they have a. Sorry. Okay, so yeah, so TrueBit. TrueBit is a project that it's not meant to do exactly the same thing, but it does allow you to extend and to run computations that cannot fit in a smart contract. And so they created a way where you can have nodes calculating something, and then you can challenge them. You can challenge them and slash away their stake if you can prove them incorrect on the Ethereum network.
So the question is, you're asking, I'm not sure if the computation, I understand there's some way that TrueBit does it, but the challenge you're saying is, I'm not sure if the computation was done correctly, and I want to re-verify it. I want to, right?
Yeah, since you want to incentivize nodes not to be compromised, so I mean, if someone managed to compromise SGX on his own machine and is using it to cause some damage, then it would be good if it had a stake that you could slash by proving this node was cheating.
Yes. So we have stake, and there is the node publication was published. So first of all, we have stakes that every worker does. We didn't cover many things. So there is this, and now the question is, how do we know that a worker should be slashed or not? So it depends on the use case, I guess. There's different ways, but essentially, you have things like availability, right, and connectivity, and you want the node to actually compute the result and commit it within a reasonable amount of time, and there's this. And then there's the computation itself that you want to know it's done correctly. So basically, if we can detect this, we have slashing conditions, and we're working on different ways to approach it. But right now, we are counting on the fact that this signing key, that there's one specific signing key that was generated inside the Enigma enclave, and it wasn't hacked, meaning Intel wasn't hacked. That answers your question.
Very much. That was